Hello everyone. In this series of videos we're going to be talking about rotational kinematics. So we'll be taking everything that we learned in our first couple chapters on 1 and 2D motion and looking at how that applies to things rotating. So we're going to start by talking about rotational equations of motion. So what we're trying to do in this session is to figure out how to describe rotation in terms of angular position, velocity, and acceleration. And then we're going to try to analyze this angular motion when the acceleration is constant. Okay. So, in translational motion, we usually represent position by just a point, such as x. But in rotational motion, position is represented by an angle, theta, and a radius, r. Now, the linear displacement is represented by a vector, delta x. But angular displacement is represented by delta theta. It's not technically a vector because you can either go clockwise or counterclockwise, but it behaves like one for very small values, okay? And it's also not a vector because it's going in a circle, not in a straight line, okay? All right, now a particle that rotates through an angle delta theta also translates through a distance s, which is the arc length of this path. And we know that this is related to angular displacement by s equals r delta theta, okay? And so that's something that we know from geometry. The instantaneous velocity of this particle is going to have a magnitude vt equals ds dt, and it's tangent to the circle. So that's vt, the tangential velocity. It's also going to rotate with an angular velocity omega, which is equal to d theta dt. And the direction of this angular velocity is given by what we call the right-hand rule. So what that means is basically if you curl your fingers with the direction of the rotation, then your thumb represents omega, the angular velocity. And then tangential and angular speeds are related by the equation v equals r omega. Now I should also mention that for this right-hand rule, we're going to be seeing these a lot in the course. And for this first one, if you curl your fingers with the rotation, your thumb is omega, and a dot with a circle around it represents that omega is coming out of the page. Whoops. And a little x means that omega is going into the page. And I should also point out that in this equation, v equals omega r, it works out because the units of v are meters per second, r is meters, and omega has the units of radians per second, which is angle divided by time, d theta dt. Now radians is kind of a placeholder. When you multiply radians by something else, it sort of goes away. Okay, so let's look at an example. Well, first let's talk about acceleration. So tangential acceleration is given by a equals dv dt, and this is the tangential velocity vt that we're talking about. And angular acceleration alpha is equal to d omega dt. This angular acceleration can be parallel or anti-parallel to the angular velocity. So remember that this angular velocity omega can be out of the page, right? Or it can be into the page. And depending on whether you are slowing down or speeding up, then acceleration and omega could have opposite directions. Okay, so angular acceleration. And finally, tangential and angular accelerations are related by a equals r alpha. So meters per second squared is equal to meters times radians per second squared. Okay. And don't forget about centripetal acceleration, right? AC is v squared over r, which is also the same thing as omega squared r. All right, so let's do an example problem. We're going to assume that this particle is speeding up, and let's try to determine a bunch of different directions, okay? So I'm going to let you try it, and when you think you have all the answers, unpause and we'll go over it. Okay, so hopefully you've had a minute or two to think about this. And so we're going to start by looking at the instantaneous velocity. And so it's actually just going to be tangential to the path here. Okay, so that's vt. Sorry, let's go back a second. Okay, so vt is just tangent to that path. What's the direction of the angular velocity omega? Well, it is rotating this way, so that's like the delta theta. So using the right-hand rule, we can write that omega is coming out of the page. Now it's speeding up, so what's the direction of the tangential acceleration? The tangential acceleration will also be out of the page. It's in the same point really as omega, but that gets kind of confusing. Okay, oh, sorry, I mixed it up. Tangential acceleration is actually same way as tangential velocity. Angular acceleration is the one that's out of the page, my bad. And the direction of the centripetal acceleration is going to be directly inwards like this. Okay, and so what's the direction of the overall acceleration of the particle? You can put that in a different color, and that's going to go kind of like this, and that's the vector sum of AT and AC. So now we can ask the question, okay, what changes if the particle is slowing down? So let me erase this and we'll just redraw things very quickly. Okay, go ahead and pause and think about this. What happens if it's slowing down? Okay, so first of all, the velocity still goes this way, vt, and the angular velocity is still going out of the page, but the tangential acceleration at will be opposite of vt because it's slowing down, and the angular acceleration, because of that, will be into the page. The centripetal acceleration will still be inwards, and the overall acceleration will be sort of back like this. Again, the vector sum of the two. Okay, so now let's talk about the equations of motion for rotational kinematics. Okay, so we started with the equation v equals v initial plus at, and instead of v we'll put an angular velocity, and instead of a we'll put an angular acceleration, and we get omega is equal to omega naught plus alpha t. Now you might remember from not too long ago, like a slide ago, that v is equal to r omega and a is equal to r alpha. If I take those and I plug those into the linear form, I'm going to get r omega is equal to r omega naught plus r alpha t. Well, of course, these r's are common, so they're going to cancel out, and we get the angular form. So once you accept that these equations are okay, then we can go from one kinematic equation to another. So we have the second kinematic equation, x is x initial plus v initial t plus 1/2 at squared, and we're going to put an angle for position, angular velocity for velocity, angular acceleration for acceleration, and we're going to get the angular form. Okay, so x turns into theta, v turns into omega, and a turns into alpha. So you can just plug those in. Okay, Finally, we have the third kinematic equation. This is the forgotten equation. Okay? So v squared is equal to v initial squared plus 2a delta x. Put in the angular velocity, and the angular acceleration, and you get omega squared is equal to omega initial squared plus 2 alpha delta theta. Okay, so let's do a quick example of this, and then we'll move on to energy. So, great album. The Beatles' White Album is spinning at 33 1/3 RPM. So that's omega naught. It's 33 1/3 RPM. We'll get back to that. And the power's turned off. So it takes a time of a half minute, which is 30 seconds, for it to stop. What is the angular acceleration of the album? Well, angular acceleration is change in omega over change in t. So it's omega final minus omega initial over t. So we should take this 33 1/3 and convert it, okay? And really what this is, RPM is revolutions per minute. Okay, so we're going to take basically revolutions per minute, and we're going to multiply that by, well, first of all, 1 minute is 60 seconds, and then also 1 revolution is 2 pi radians. Okay, so the conversion is 2 pi over 60 to turn that into radians per second. Okay, so omega final is going to be 0 if it stops, and then we'll have 33 1/3 RPM times our conversion factor of 2 pi over 60, and then that's just all divided by 30 seconds. So alpha will be negative 0.116 radians per second squared. You can check the units, but there really are radians here and 60 seconds here, and that RPM is going to go away because of our conversion. So we get radians per second squared, which is the correct unit for alpha. Okay, so next time we'll look at energy in rotational motion.